2021, and it was too humid. So it's a real throwback lab, kind of very much not related to the topics of the last week or two. Electric charges, electric attraction and repulsion is going to be tomorrow's lab. Like I said, the lab that we intended to do in the first week when we were talking about charged particles, things like that. And it was just, the demos weren't very effective at that time of year with the summer humidity. So that's going to be tomorrow's lab, kind of just a side step. Probably won't take the whole time. Just while speaking about lab, I'll say we're kind of a little bit of at a transition point in the labs right here. Most of the labs, basically all the labs we've done up till now have been circuit-based labs. And then the last 2 weeks, there's still been maybe some wiring around, but the focus has been on kind of magnetic interactions, magnetic force, magnetic field created by a current, or maybe an electromagnetic induction scenario where you are inducing a current somewhere, or you are moving a coil around nearby a magnet, something like that. And we've had, let's see, we've had 8 weeks, we've had 8 labs already, and there's only going to be 13 labs. So there'll be quite a few Thursdays in the second half of the semester in quad 2 that we probably don't have lab. There's Thanksgiving week, that comes to mind. The last week of the semester, we won't have lab, and there'll be another week, another Thursday, probably between now and Thanksgiving, where we don't have a lab. Haven't quite picked exactly which one. So what are we going to be doing with our remaining labs? There's going to be some AC circuits, but maybe not for a little bit, and there's going to be some optics labs. Think about 2 optics labs, about 2 AC circuits labs, and then this one tomorrow, which is really a throwback to electrostatics, like the rubber rod and the glass rod and maybe the Van de Graaff generator. One of the things we're going to get into in a couple weeks is the connection between electromagnetism and light. Electromagnetic interactions end up having a lot to do with another branch of physics, another branch of science, which is study of light, behavior of light, and optics. So we're going to have a couple of labs where the equipment isn't circuits, it's not batteries and wires and resistors and capacitors. We're going to have a couple labs where the equipment is a laser or just a beam, just a light bulb, lenses, mirrors, things like that kind of mix of ingredients, basically. So that's a little preview for lab. And like I said, Friday we'll be doing review for a test Monday. What am I envisioning being on the test? Circuits and magnetism, probably about 2 questions for each of those, probably about 2 circuit questions, and 2 magnetism, magnetic field, chapter 32 questions. And I'm kind of just emphasizing that because today, right now, we're going to, 1, 2, 3, 4, 5. Right now, we're going to start by starting to talk about electromagnetic induction for today. And we will pick that up again pretty heavily a week from now after the test. And I'm going to, I'm going to kind of do one demo. This will not turn on. Okay. I'll turn on the document camera at the moment. Power. Power. I don't know where the other end of this is to check the other end of the power cord. Okay. Let's see here. Can I get the display on? Maybe. Yes. Okay, let's do that. Okay. So there's going to be one kind of conceptual demonstration where we kind of talk through the concepts once, and then I'll start to do some calculations with a quantity called magnetic flux, which is the main new quantity that shows up in chapter 33 and in the discussion of induction that hasn't previously been introduced. So we have magnetic field, capital B measured in Tesla. Of course, we have forces or torques measured in appropriate units for force and torque. And now with chapter 33, we're going to talk about a quantity called magnetic flux. You can talk about the same concept with electric physics and talk about electric flux. And we'll do some calculations of that. But I want to kind of refer to one of the more basic demonstrations from one of the more basic stations from last week's lab where you had the 6 stations that you rotated through. So let's talk about this situation. Boy, what am I going to do if I can't get this document camera on? Nope, that seemed to do it. Push that cord in 4 times. Okay, so the demonstration we're going to refer to, which is kind of one of the more basic ones, initial ones that was done, and the people that did these kinds of things are people like Hans Oersted and Ampere and Faraday. Faraday did a lot with induction. We're going to talk a lot about him. So the demonstration will be, well, maybe I'll kind of do this so you can kind of see it. So we have our coil here. Imagine this is connected, so there's a completed circuit. Of course, right now there is no completed circuit, but let's say you took a wire and connected it from there to there. So there's a completed circuit. We've got a large number of turns, and then we did things, I think this was called coil and ammeter station. And the main things I'd like to consider, like what happens to, is there any effect on the coil when, let's say, you point the North Pole like this and you bring the North Pole towards this? So you're moving it towards. And then we could consider variations. What if instead you move the North Pole away? What if you kind of had the South Pole pointing towards the way? But for right now, let's say the North Pole is pointing, that's the near pole is the North Pole, and it's coming towards. And questions we'd like to be able to answer based on Faraday's law and Lenz's law and the concepts of induction is we'd like to be able to answer, will there be any current in the coil? So will there be any current in the coil when we do that? And if so, which orientation, which direction will the current go? So I'm going to kind of turn it to this view and imagine the North Pole is pointing, away from the viewer and it's heading like this. Will that create current flowing this way, which may be on the ammeter, made the needle deflect one way and get detected as a positive current, or will it make current kind of go the other way? Will make current kind of go the other way. So clockwise or counterclockwise would be one way to talk about it. I think I'll kind of sit in this view. So from this perspective, I think the 3 main options would be I move it towards and there's no current. I move it towards and there's current kind of heading up the front face, in at the top, out of the bottom, circulating kind of like that, away from the viewer here, at the viewer there, or maybe the opposite of that. This current circulates the other way and it's out at the top of the page, or out at this portion of the page, down the front face and in there. And in order to kind of think those things through, you need to know a little bit about right-hand rule, maybe not surprisingly, but that's not the only thing. That's going to show up somewhere along the way, but it's really not the only thing. And there's a new concept that's going to be kind of at least as important, which is thinking about flux and thinking about Faraday's law, which we'll talk about here. Let me just kind of get this under here, right on there. Okay, so here is what we need to do. Faraday's law says you need a changing flux, whatever that is. You need a changing magnetic flux to create, or the word we often use is induce a current. That just means create, result in a current. To induce an electric current or an electric voltage or an electric fill in the blank. Okay, so this is the thing we're going to do calculations with. Magnetic flux. What's magnetic flux? For right now, basically, basic definition, and we'll refine this. Oops, I didn't mean to write B yet. Basic definition is flux equals field times area. So what's the area we're going to be talking about? The area will be the cross-sectional area enclosed by the loops, very commonly. So like we talk about the flux through a 2D surface. What's the flux through the chalkboard, like the front panel of the chalkboard? So you pick a 2D surface, probably a flat 2D surface, but in general you pick a 2D surface and you say, is there flux through the chalkboard that way? Is there flux through the chalkboard this way, or is there no flux? And we'll put numbers to this, but for right now, what we mainly need to do is figure out, is there a flux? And if so, is it increasing, staying constant, or decreasing? So which direction is the flux, and is it increasing, decreasing, or constant? That would be enough to answer questions like, will there be a current? And if so, what orientation will the current flow? So in this case, which field are we talking about? We're talking about magnetic field. So what is the units of flux? It looks like it would be Tesla time area units, so Tesla meter squared. So if I do this, I would say I'm going to kind of have a little kind of direction of flux is a question we need to consider. And then the second question to consider is change in the flux. I'm going to put a question mark here. Change in flux, question mark. And then if we answer these two questions, if we have these two questions thought through and we kind of understand the answers to those two questions, then we can say, yes, there's a current, it's clockwise. No, there's no current. Yes, it's counterclockwise. And here we go. So let's say we do this and we have the North Pole right here. What direction is the flux through these loops? What in the vicinity of this test object, what direction is the magnetic field due to this source? Well, magnetic field points away from North Pole. So in this scenario, I have, I'll kind of sketch it out here. I'm just going to show one coil, but you can imagine many of them. And right here, oh, there's a couple of them at least. Right here, we're going to have magnetic field, of course, pointing out the North Pole, which is leftward. So we're going to have magnetic field kind of like this, and then it kind of comes up and goes like this, and then it goes down like that, and then maybe a couple more. I'll throw in some more. And then some do this, and some do this, and all these are kind of pointing this way. So, so my magnetic field is this, the flux and the field direction are the same. Flux and field aren't the same units, but if field points to the left, then flux is leftward. So I'm going to say the direction of flux, or you could say almost flux slash field, kind of almost using them interchangeably, not when talking about the amount, but when talking about the direction. The direction would be, let's say, leftward. And basically, for the purposes of doing the calculations, you could think of leftward flux as maybe being one sign of flux and rightward flux being the opposite sign of flux. Okay, and then that's true if the North Pole's if the magnet's just sitting here, but now I need to do something. I need to do something which gives me a change in the flux down here at the bottom. I need to do something that changes it. So I might move the coil, I might move the magnet, I might spin the magnet, and I've chosen to move the magnet towards it. So what's going to happen to the change in the flux? And basically, what I have in mind here for change in flux is it increasing, decreasing, or constant? So there's a leftward flux, and if I bring the North Pole closer, some of these field lines that didn't used to go through the coil are now going to go through the coil. And not surprisingly, when the North Pole is close, you're in a strong leftward field. When it's far away, you're in a weak one. So we have an increasing leftward field. And if we've answered these two questions, now we're ready to think through like this. These are kind of the cause, and here's the effect. So this is the magnetic cause. And now here we're going to kind of work through in two steps. What's the effect? Is there an effect? And what orientation? And so what I've said here is Faraday's law says you need a changing magnetic field to induce an electric current. Flux is field times area conceptually. There's some vector stuff in there to get the amount correct. And now Faraday's law has a minus sign in the equation. And the minus sign in Faraday's law is often just kind of expressed as its own statement. The minus sign in Faraday's law is often called Lenz's law. So conceptually, this should be kind of written after Faraday's law, but I'm going to write it up here. Lenz's law doesn't get you the magnitudes of things, but it gets you the directions of things. And it says the electric effect is always in a direction to, and the key word here is oppose, opposite, against, oppose. You can word Lenz's law in many ways, but it's always going to have that concept in it somewhere. The electric effect is always in a direction to oppose the change that created it, that induced it. You know, so kind of conceptually, it's like this. Do you have a changing flux? If you do, expect there to be an effect. And then what direction will the effect be? It will be in a way to try to oppose the change. So what's the change in this case? Increasing leftward flux. So what is the opposite of increasing leftward flux? Does the loop is, so, and I'm going to say induced flux / field, kind of a little bit of a mirror of the direction of flux / field. Will there be an induced flux or field? Well, it's kind of like, let's just make up a made up number. Let's say when the North Pole is that far away, that the flux through the coil is 100, just whatever that means. There's just like 100 units of flux to the left. The basic idea is the coil likes the number 100. And as long as the number stays at 100, the coil doesn't respond. But if the number starts to change from 100, it'll respond. So let's say we have 100 units of leftward flux, and now we bring the North Pole here, and now we have 170 units of leftward flux. It doesn't like 170. It wanted to stay at 100. So what does the coil do? So I've got some red lines on here. I'm going to extend them a little bit. This is you might call this the applied field. And that is due to the magnet. But in addition to the applied field, there's going to be a second magnetic field show up. And the second magnetic field is going to be due to current running around these coils. In which direction will the new magnetic field point? It will be opposite to the increasing leftward. So it will want to create rightward flux to bring the number back down to 100. It won't accomplish that goal, but that's the kind of direction it wants to go. So it's going to have an applied field, and then there's going to be a response field, and the response field will go through the coil this way. And let me just kind of do that. And I might call this the induced field, or the response field, or the secondary field, something like that. So there's kind of a primary and a secondary. So question 1 is the direction of the applied flux or field. And question 3 is, what will be the direction of the induced flux or field? And the answer is, it's going to be rightward. And that all this means like through the coil rightward, through the coil leftward. So what's the last question to consider? What direction is the current? Direction of current flow. And this arrow here to take you from above the line to below the line, that's Lenz's law. This is how this is the point at which I applied Lenz's law. 1 and 2 are basically just knowing the definition of flux. Going to step 3 is kind of thinking through Lenz's law. How do you get from 3 to 4? Right-hand rule. Or in this case, maybe apply chapter 32 concepts to fill in the last step. If you have a coil sitting here like this, and it's got its own magnetic field pointing that way, which direction is current going around the coil? And that's a good right-hand rule, a chance to use right-hand rule. So the current is going to go around the coil, kind of down the front face, because I do my right-hand rule like this. Not with the red field applied by the magnet, but with the green field response from the coil. So this might be right-hand rule, or in general, this step here is right-hand rule, or maybe a chapter 32 idea. And in this case, how could I say that? I could call that clockwise or counterclockwise for the direction of current. I think I'll just say down the front. And you could express it in different ways. So get a magnet on here. North, south. So that would maybe one thing, maybe with the coil and ammeter, that would be just detected as a positive current, let's just say. So what's a new scenario that we could consider? What if you put the North Pole, and what if you put the magnet very close by and you sit it still? I'd have a leftward field. I would have no change in the flux, and there'd be no change to oppose, and there'll be no current. What if you put the magnet inside the coil? You do this, and you're like, I'll just put it in there and let it sit there. It's in a very strong magnetic environment. There's a lot of chapter 32 stuff going on, and there's no chapter 33 stuff going on if you just set it there. Did you see some examples of things like that Thursday? Maybe. So what kind of things could I do with, what kind of things could I do to get a greater down the front, let's say positive current? If you move it faster, I'm going to have a greater increase. I'm going to go from 100 to 170 in a tenth of a second instead of 100 to 170 in half a second. And this is all about time derivatives of things. Whenever it says kind of changing, that's going to show up in the math as not flux, but derivative of flux with respect to time. So move it faster. What else could you do? What else do you think, based on either just the diagram or just thinking of Thursday, could you do?
Stronger magnet or coils?
Stronger magnet, probably stronger magnet. If you had a stronger magnetic field, instead of going from 100 to 170, if you're going from 200 to 200 or 340, and probably more. If you had a bigger area, that could also do it, but you'd have to kind of be a little careful of that, because if I just make the coils bigger, but I don't make the magnetic field from the source any bigger, it might not actually result in greater current. Because one thing to notice in this picture is, what if you just make these coils bigger and bigger? You leave the magnet sitting right where it is. It's the same strength magnet. The red doesn't change. You just make the coils bigger. You actually have, at some point, you're going to get to the point where these guys are kind of curling back this way. These guys are curling back the magnetic field. So you're going to get a lot of leftward magnetic field in the middle of the loop, but you're actually going to get some kind of canceling magnetic field as it loops its way back to the magnet. So anyways, but bigger areas could do it. But that would kind of probably mean not only you could make the magnet stronger, or you could kind of have like the same strength magnet and make it a physically larger region of that magnetic field. Or you can move it faster, and maybe not too surprising, I think you probably saw this. We have a 400 turn coil. We had smaller number of turns. It's kind of like you get a certain amount of bang per turn. And if you have 50 turns, you get 50 times the voltage basically, and probably you get an increased current. Okay, so what if we did this? What if you put the North Pole here and you pull the North Pole away? At what point does this kind of, how much of this do we have to change for the new question, like the part B question? It's still leftward, but now it's a decreasing leftward flux, and the opposing decreasing means I'm going from 100 down to 30 and I want to pump it back up to 100. So in that case, the green field due to the induced current would be in the same direction as the red field. And that would flip this and we'd say, okay, now I need to, so it's kind of like the current will flow around the coil in whatever direction it needs to try to reestablish or maintain that 100 value that it felt a second ago. And in that case, then the magnetic field in green would switch to be this way. And then with right-hand rule, that switches to be kind of up the front current. So one thing to not skip over, here's a little bit, here's almost the right application of chapter 33 concepts, but not quite. Here's almost the right idea. Red field points left, therefore green field points right, therefore I do right-hand rule and the current is down the front. That's not quite enough, right? Because depending on what I'm doing with the magnet, that might be the correct answer, might be the opposite answer, or there might be no current. What do you think would happen if you, so you always have to, you can't go straight from number one. I know the direction of red and I'll oppose it with the direction of green. You got to know the direction of a change. You know, it's kind of like, which way does the drag force or like the air resistance force on an object point? Opposite the motion. You can't just tell me the object's east of the origin and say, oh, well, that means the drag force is west. No, no. I don't care where it is exactly. I just care how it's moving. If it's east of the origin and moving east, yeah, then the drag force is west, or the friction force or something like that. But if it's east of the origin, I don't really care. If it's sitting still, what direction is the drag force? There isn't any. If it's east of the origin and moving west, well, then the drag force will be east. So, and again, it's kind of like, tell me not the value position, tell me the derivative of that value, and then I can tell you what the response will be. And the bigger the derivative of the value, the bigger the strength of the response will be. What do you think would happen if you took this guy and you went from this orientation, kind of, we often have like an initial moment and a later moment, or a process taking us from a change. What if you took this guy and you rotated him like that?
Magnetic field is like almost twice the change, you just moving it closer, because it's literally opposite now.
So what if you took this guy and rotated him? Let's say not all the way. Let's say we rotated him from here to here.
I feel like it's something
At some point, to do a detailed calculation, it would maybe get a little hairy, but could we at least think through the general issue of, will there be current in the coil, and if so, what direction? If you go from here to here, do you think there'll be, flux is kind of like the number of red lines that pierce the loop. So like the initial flux is how many red lines pierce the loop right now. And the new flux is how many red lines would go through the loop if you kind of tweaked it up 45 degrees or something. And do you think that would be an increase in leftward flux of the loop, constant leftward flux, or a decreasing leftward flux? It'd be fewer lines through the loop to be tilted out of this orientation to really almost any other orientation if we don't move the magnet, if we kind of keep it that far away. So this is a little bit less leftward flux, would be the reverse of these responses here. Leftward, slightly decreasing, so we'll get a slight rightward response for magnetic field due to the coil, and that means we'll get a slight, decreasing, so leftward, so up. What if you went from here to here? That would be a really big swing, because we kind of went from like 100 positive units of magnetic field flux to like 100 negative units of magnetic flux. And our change was a very big decrease in leftward flux, because we went from positive 100 to 200, so a very big decrease, and we get a very large response opposite to what's written in green here. What are some other ones you could consider doing? So the main three things we consider doing are trying to increase or decrease the field by, like, maybe in this scenario, moving the magnet closer away, trying to change the orientation, which is something we're usually pretty interested in. Like, what did you do to light the light bulb at that station, you know, near the back of the room? Those big magnets, those big horseshoe like curving things, those are magnets, and there's a strong magnetic field from like the bottom of one to the bottom of the other. I don't know which one's north and which one's south. We could get on and figure out. It doesn't really matter because there's a strong horizontal magnetic field. And in that region, you're tumbling a coil. And so you're not really changing how strong the magnetic field is by bringing things towards or away. You're not changing the area of the loops. The area is the area, but you're kind of rotating them. And as the area comes into one alignment and out of one alignment, you have a changing flux. In fact, as you rotate it, you have a continually changing flux, which means you're going to read off you're going to continually be producing some current, some voltage and current around the loop. And if you connected some outlet to that voltage, you could do something with that voltage, just like with a 9-volt battery, you could do something with the 9 volts. Here's a bit of a funky one. I'm going to get a different loop. Not that one either. So here I've got this loop. It's kind of flexible. Let's say this loop is in the position of this guy, and I kind of just did this to the loop. I very quickly just kind of like went from this rectangular shape to pretty flattish. So I'll kind of change the scenario up. Let's say the North Pole is pointing away from me. So the green is, I don't know if you can kind of see, the green is towards the camera, red's kind of away. So let's say the North Pole is pointing towards it and I don't move the magnet. And maybe I hold it fairly close by, but I hold it there. And then I just kind of like, boom, and I try to like squash the loop. Do you think there would be current flowing around the loop while that's taking place? So let's just go through our 4 steps. Right now, what's the direction of the flux through the loop? Well, North Pole is down, so magnetic field, just imagine this is a much larger, physically larger magnet. So there's a bunch of downward magnetic field into the loop, like into the page, field and flux. What happens to the flux as you flatten the loop? You get less and less flux. So we have a decreasing into the page flux due to the source. That's my choice. That's what I have direct control over. It's kind of the experimenter. I have a decreasing into the page flux. So the loop will respond with trying to reestablish more into the page flux. In that case, the induced effect will be downward as well. And then I do right-hand rule. And if I want a downward field in the loop, I circulate counterclockwise. Sorry, clockwise, said that wrong, clockwise. And that could happen. That's probably the least common one, is changing the area. The more common ones are manipulate the magnetic field strength, maybe by moving the magnet closer or further, moving things around, or manipulate the orientation, which plays a role as well. So here are some things that people did in the early days to get a really large effect. They'd have one coil over here. They have one coil over here. And this one would kind of loop off to a battery. Oh, but there'd be a switch in the circuit. Okay, and let's just say it'd be more clear from the connection. Let's say like this is the positive terminal, this is the negative terminal. And this is coil number 1. And then over here, maybe we have another coil. and this will be coil number 2. And this one maybe has an ammeter in it. Let's just say there could be a resistor here, there could be a light bulb here. I'll say there's a light bulb. That's supposed to be like the filament of the light bulb. And there we go. And it kind of comes up into there. So here we have the battery connected to one set of wiring. Here we have something physically not connected. There's no electrical connection, and we have another circuit over here. And the question is, the process would be this. What do you think will happen here when you, let's say you do this. The switch is like this, and you wait a couple seconds and you close the switch, and then you wait a couple seconds. What will you see over here? And again, maybe I'll do two things. There'll be like, there could be a light bulb here, or there could be one of those needles like we had at the front table that can kind of swing and show you physically, you know, show you very dramatically there is or is not a current, and if so, the orientation. What do you think you'd observe here if you had this set up and your switch is open, you close the switch? What would you observe over here from the needle, or what would you observe over here from maybe the light bulb?
Right in there, again.
You'll get some light, you'll see the needle move, but it won't move for long. Why won't it move for long? It's perfectly happy with the switch open. With the switch open, there's no current, there's no magnetic field according to chapter 32, and you have a nice steady magnetic field through all the purple turns. It's 0, 0, 0, 0, 0, 0, 0, 0. And then you close the switch, and within a very short amount of time, you all of a sudden go from no magnetic field through purple to a fairly strong magnetic field through purple. And let's just say, I think it'd be a little more clear. Let's just say like you could look at the way the wires connect over here, and you could see that this guy kind of heads up the front. You know what I mean? Like this wire kind of goes up the front and wraps in a certain orientation. So when you close this switch, what happens to the magnetic field? It goes up the front. So the magnetic field from black points leftward. So we get a strong magnetic field kind of this way. We get a strong magnetic field this way applied. And thus we all of a sudden have a very, very strong kind of out of nowhere leftward flux through the purple coils, and they don't like it going from 0 to high leftward, so they respond with rightward. And they respond with rightward, and that means that the current would kind of flow down the front face of this guy, and that would be detected as one sign of current. What if you did this? What if the switch is open? You wait 5 seconds, you close the switch. You wait 5 seconds, you open the switch. What would we see kind of if we had a graph over here of time and current, meaning current in coil number 2. So like, let's say at time 0, you close the switch, and at time 5 seconds, you open the switch. What they saw is things like no current while the switch is open, no current while the switch is open. In between, there's not really much current to sit there for 5 seconds and have a really strong current flowing here with a really strong red field, but strong and steady. So in between, it's pretty much 0. But what would you see while closing it? I'm going to kind of say, while closing it, you would briefly see like some negative current, like a spike of negative current. And then while opening it, you would kind of see a spike of positive current for a very brief interval of time. What do I mean by positive and negative? I maybe should be more clear. I'll say the positive direction, I'll say up the front is positive. Up the front is positive, down the front, or you could use like clockwise, counterclockwise, so no, that would be negative. And I think we'd have something like that. What would the graph of flux through this surface look like? What would the graph instead of flux and time look like?
0 seconds, 5 seconds. What would the graph of flux through this guy in time look like? There'd be no flux while it's closed and no flux while it's closed. But while it's open, but in between while the circuit is closed, we have this large current, and this would be kind of like leftward flux. And it would be a very high value, and it would ramp up in a short amount of time, very short, and would ramp down in a short amount of time. Does that kind of sound about right? How do these graphs relate to one another? When that one's flat, I don't care how high the plateau is. If that one's flat, there's nothing over here. And when that one's steep, you get a big amount of something over here. And then, so basically what are we saying? The effects are proportional to the derivatives of the causes, if we identify flux as the cause. Then there's one little tweak, and I tried to get this right with the way I oriented things. When this has a positive slope, when this slope is positive, I drew a negative current. And when this slope is negative, I drew a positive current. And you'd have to kind of assign directions to know what's meant by that, but I think this is kind of written correctly here, but you'd have to look at the orientation of the wrappings. But the basic idea is the current over here is proportional to the time derivative of the flux with a minus sign. So, and we could think of this as either current, and the way Faraday did it is he focused on the derivative of the flux with respect to time. So flux, the symbol is a capital Greek phi. And instead of writing current, he said, well, here's the voltage. So the cause is a d phi dt, and the effect, the electric effect, is a voltage. But if you have a completed circuit and you have a voltage, then you just kind of can use resistance to figure out, 7 volts is how many amps and vice versa. So we often, I'm here plotting current, but what he would more naturally plot is voltage. Well, if you have a voltage trying to drive current a certain direction, then you can just divide that by resistance and get the amount of current that flows. So this is the magnetic cause. And basically what we're saying is Faraday's law is basically saying the cause is proportional to d phi dt with a minus sign. And the minus sign is Lenz's law. Lenz's law is just like this kind of rule of thumb, this kind of guideline for helping you figure out orientations or signs of things. It's Faraday, Lenz's law is kind of like on the level of like saying like charges repel, unlike charges attract. It won't tell you how strong they are, the effect is, but it'll tell you if there's an effect, kind of the direction of it. Okay, so let's take a little bit of time to think about units and figure out what kind of constant we need in this equation. Do you know what I mean by that? This is a proportionality, it's not an equation. You could make it an equation by putting a constant in here, and then we might want to think through what are the units of that constant. Okay, what's the key constant when doing electric work? Well, electric field, electric force, electric potential energy. What's the key constant there? I'm like a constant that shows up in a lot of the equations, like a lookup constant. Capital K, or you could say epsilon naught, because they're kind of reciprocals essentially. So what are the units of that constant? Let's say for K, the units are Newton meters squared over Coulomb squared. Something like that. What's a key constant that shows up quite a bit in chapter 32 for magnetic, in magnetic physics? Epsilon naught for electric stuff, mu naught for magnetic stuff. What are the units of mu naught? Tesla meter over amp. And now this is kind of like a third phenomenon. The first phenomenon is charges attract and repel. That kind of comes in with a certain constant, let's say epsilon naught, or 1 over epsilon naught. Another kind of interaction is currents create forces on other currents, and they kind of have this wrapping magnetic-y stuff, and that comes in with a constant which is mu naught. And now this is a third thing saying the magnetic stuff can actually create electric stuff. And this might have a constant. So let's think about the units of the constant. This will get us into diving into units quite a bit. So basically, this is kind of like asking, how do volts relate to flux units over time units? And let's just think this through. Units of V, and then eventually I'll put some space. I won't need much space to do that. Units of derivative of flux with respect to time. One of these will take more to work out than the other. What are the units of volts? What is the units of a potential? Well, volts, right? And let's just try to unpack this a little bit. What are some equivalent units to volts so we could just kind of see the connections to d phi dt more quickly, perhaps. What's a volt? How does it relate to joules, newtons, meters, seconds, things like that? Let's see. Let's maybe try to get it in terms of newtons. Any thoughts? How does volts relate to joules or newtons? Yeah, somebody's got that now. What are you thinking?
That a volt is equivalent to a Newton meter divided by Coulomb.
Yeah, okay. I'm just going to grab the front of this. Daniel was looking at notes he put on the back here for test one, probably, maybe. So I think the answer is there. But if you just kind of think in terms of here, like how do volts relate to, joules or newtons? And we go either way. I think let's go for newtons because I just can do that kind of easier. Volt times a meter is a joule. Volt times, sorry, nope. Volt times a coulomb is a joule, and a coulomb, volt times a coulomb is a joule, and joule divided by meters gives you this, something like that. Going this way, you divide by distance, like dv dx. You divide by distance, du dx. Maybe there's a minus sign, but dimensionally, you divide by distance. And going this way, you multiply by charge. So something like that. So maybe we could say, here's a couple true statements. Volts is volts. It is a joule per coulomb. A joule is a Newton meter per coulomb. Yeah, we could go one more. Maybe I'll just go one more, but I think I'm going to focus on newtons. What if I wanted to unpack it down to like kilograms, meters, seconds, and coulombs, like the four really basic ones? Well, a Newton is a kilogram meter per second squared times meters over coulomb. So there it is, kind of really unpacked, but I think maybe let's focus on this one. Okay, what about d phi dt? Well, d by dt, that's not too hard. That's units of 1 over seconds, right? What about flux? And although I haven't, basically the equation for flux is magnetic field times area, generally speaking. Magnetic field times area. And there's some directions in this. I'm not including the directional vector stuff right now, but magnetic field times area. So what are the units of flux? Tesla meters squared. But just like I don't want to stop on volts, I kind of want to get to something else. I don't want to stop on Teslas. How do you express Teslas, units of magnetic field, in terms of more familiar quantities like joules or newtons? So I'm going to say, like, here's one equation that I might use, or at least one proportionality or approximate equation I might use. And then I'm going to say, what about this equation? Can you think of an equation that has both an equation that has both something measured in Tesla in the equation and also has something measured in newtons in the equation? Like here to here is kind of like delta V is delta PE over Q. Here to here is something like work equals force times delta X, maybe something like that. I don't know. It can kind of get me from one of that. What's an equation that has both Teslas both the quantity that Tesla's is the unit for and the quantity that Newton's is the unit for. So what I was thinking is magnetic force is QV cross B. Yeah. So what's a Tesla? Well, a Tesla, a meter per second, a Coulomb gives you a Newton. Yeah. So let's just solve that for Tesla and put it up in there. So what's a Tesla? Meters squared, whatever a Tesla is over seconds. And what's a Tesla? Newton times seconds. Yeah, Newton times seconds over Coulomb times meters. That look about right? Okay, and now let's just kind of clean this up. Meters squared over meters, Newtons, so I have a Newtons on top. Meters squared over meters, I think I have a meters on top. I have a 1 over Coulomb, and I have a 1 over, I have a seconds here and a seconds here. I was messing up the seconds. What happened to the seconds? They canceled out. So what are the units of d phi dt? Newton meter per Coulomb. What are the units of volts, or this thing called electric potential? It's Newton meter per Coulomb, which is not super obvious if you just are used to thinking voltage is measured in volts, which is absolutely true. And there's a name for the units of magnetic flux. It's called Webers, or you could say Tesla meters squared. Either way, it's not super obvious that the units of flux are flux units over time units is volts units. So if there's a constant in the equation, what's the dimensions of the constant? There's no units to this constant. So it could be a constant like what kind of thing? 2 pi, 1 over 4 pi, 7, 1/2, something like that. And basically there is no constant, depending on how you think of it. Basically there's no constant. The number of wrappings does matter, and you could either incorporate the number of wrappings into your calculation of flux, but a lot of people would say flux is like, I'm going to use flux to mean the flux through 1 wrapping, and at some point you need to multiply by the number of wrappings. So either you could say the constant is -1 for 1 wrapping, or you'll see people write it as -n d phi dt, for n wrappings. But basically there's no lookup constant. There's no epsilon naught or mu naught to look up in chapter 33. It's just multiplied by number of turns. So basically this is Faraday's law. It is often, so you got to know how to calculate fluxes, and you got to know how to take derivatives, and you can calculate induced voltages. What if the question asks for an induced current? Maybe you just do a basic circuit step like saying voltage is current times resistance, depending on if they want you to report a voltage, which is more natural to Faraday's law, or if they want you to report a current. Fundamentals of circuits, chapter 32, chapter 33. Chapter 33, section 3, it's called magnetic flux. And they're going to talk about it here. And then chapter 33.4, section 33.4, Lenz's law. And there's not an equation for Lenz's law. There's a statement, like a 2-sentence statement. There is an induced current in a closed conducting loop if and only if. So you get an effect when the magnetic flux through the loop is changing. So flux is not at a point, flux is through a surface, like a loop. Is the flux through the loop constant or changing? The direction of the induced current is such that the induced magnetic field opposes the change in the flux. Yeah. And then section 33.5, Faraday's law. And here they've written Faraday's law without the minus sign, and they'll write it usually without the minus sign. And how are they writing it? Slightly different than how I wrote it. V equals -n d phi dt, or you could say V equals -1 d phi dt. they're writing it by taking absolute value, they don't have to write the minus sign. But what are they writing instead of voltage? This big squiggly guy, big squiggly E, which stands for electromotive force, or EMF, which is more or less a synonym for voltage. It's measured in volts. It's basically a voltage. The slightly weird thing is, so you could say, what's the battery's voltage? Or you could say, what's the battery's EMF? And that basically is the same thing. They might be used in some contexts slightly differently. Like you could, yeah, but basically that's voltage. Historically, there's just lots of different names for this key concept in electric physics called potential difference, voltage, EMF. There might be more. And it kind of probably comes from the fact that voltage in circuit analysis plays a role that reminded people a lot of the role played by force in like Newtonian mechanics analysis. The EMF is induced around a closed loop if the magnetic flux through the loop changes. The magnitude of the EMF is this much. And what about the direction? The direction of the EMF is given by Lenz's law. Basically, it's the minus sign. You just have to be kind of careful when you put the minus sign in there, because it's like, well, what do you mean by a negative voltage? Is that this way or is that this way? And thinking that through is basically redoing the Lenz's law thinking. Okay. What is the formal definition of flux? The formal definition of flux is given right here. Magnetic flux, can you guys see that? Like, I don't know why that is so small. I guess I'm zoomed out. Magnetic flux is the area vector dot product the magnetic field vector. So we're back to this idea of a loop or a coil having an area vector. And we've kind of said this a couple times, but we're going to keep saying it. If I hold a loop like this, it has a certain area, you know, some number of meters squared, some number of centimeters. If I hold it like this, what direction does the area vector point? The area vector points perpendicular to the loop. And if I want to say the area vector points that way, that's kind of making the choice of thinking of like this orientation as the positive orientation. Via right-hand rule, if I say the area vector points in the direction of my thumb, that's associated with kind of thinking of this orientation as the positive orientation for currents and voltages. And if you want to say it's that way, that's kind of the same thing, but now we're kind of thinking of the opposite orientation as positive. So A dot B, if there's some vector stuff here, and this is kind of, this is true, and I'm just going to read the notations here. Equation 33.9 really is a dot product, and we can define the magnetic flux more concisely as this dot product. Writing the flux as a dot product helps to make clear how the angle comes into play. When would you use this definition of, when would you use this fact for flux? You can use this one whenever the magnetic field is uniform. It's the same strength magnetic field everywhere across the loop. What is a more general statement? A more general statement would be this guy. Instead of doing flux time dot area, you do flux dot dA. If the magnetic field is a constant and it's the same strength at every point within the loop, what happens to the B in this integral? It's a constant, it can move out front. And then you're just integrating A, all the dAs. And if you integrate D anything, what do you get? Anything? Like, what's the integral of dt? Delta t. What's the integral of dx? Like delta x. So if magnetic field is the same strength at all these spots, if the magnetic field is the same for this little patch of square centimeter, this little patch, this little patch, this little patch, then you're just saying the magnetic field strength dot the full area. And that's mainly what we'll be doing. More often than not, I think we'll probably have uniform magnetic fields, and then you don't need the integral, but you do need the dot product. I think we'll do a little bit with the dot product calculations on Friday. I just want to kind of show one picture here that we're going to go through on Friday. So this has got nothing to do with magnetic field, but what is this supposed to look like? Got to get further away. Okay, this is supposed to look like a roof in the winter or at some point. So you see what this is kind of saying here? That's the sunlight coming in there. And let's say it's the middle of the winter and there's snow on both of these roof surfaces. There's been snow at the start of the day on both roof surfaces. Which of these roof surfaces do you think will have more snow at the end of the day? If it's a fairly bright sunny day. What's that?
The right side will melt first.
The right side will melt first, probably. And I have pictures of this from my apartment where like you can kind of just see the building. And of course the building extends kind of into and out of the page a long ways. But the basic idea is, what's the area of this roof panel? Same as the area of this roof panel, right? It's not like one's bigger, and so it's picking up more energy because it's bigger. How bright is the sunlight at this roof panel? Well, same as the brightness of the sunlight at this roof panel. And in the analogy, what would the brightness of the sunlight be analogous to for our chapter 33 considerations? Magnetic field. So like we have the same strength magnetic field hitting both the same area, but what's different about these two? This is going to pick up a lot more energy every hour, and it's going to melt more snow, let's say. And why is that way? Why is that true? Because we would say that the area vector for this face, is closer to parallel to the incoming magnetic field, whereas the area vector for this face is not very close to parallel. And dot products give you a big amount when they're parallel. So that's what the dot product is kind of about. It's saying like you're not orienting the left roof very well to pick up a lot of energy from this certain incoming direction. And that would be kind of like A dot B, area dot magnetic field. We'll do that. And this one's going to be bigger because that's closer to kind of parallel or anti-parallel, closer to the same line.
Ask you a question about the lab.
One of the 6 stations.
Yeah.
Yeah.
So what do we need the mass of the magnet
For which part? Which
for the
dropping it through the aluminum pipe?
terminal velocity?
It might be nice to know the mass of the magnet, and of course they have different masses, the 3 different things you drop through there. In particular, one of the magnets had like the black kind of rubbery coating, and one of them was smaller and just silvery. You don't need to know the mass of the magnet. If you were to just, measure the length of the pipe and record how long it takes to fall through.
I suppose, yeah.
Yeah, and basically we're just kind of assuming that it goes from speed 0
Yeah.
to whatever the constant final terminal velocity is in a very short.
Assuming it's constant acceleration.
It would be pretty constant, but actually it wouldn't be constant. But I think basically it's going to reach that final velocity within like a centimeter or 2. Does that seem kind of to agree with what you observed just looking down in there?
What do you mean? What?
Like, did it look like it was speeding up?
No. How good it's going?
Like probably very soon after it was dropped, it looks like it's probably kind of settled into some speed, and then it's just kind of moving at that steady speed. So basically, it was just to kind of measure the time and the distance over time. And probably the different magnets had different terminal
So the only
velocity.
thing is the direction of the current in the aluminum tube
That's pretty tricky.
and the direction of the pendulum rings.
So
because
it has to
both
go-
ways, the magnet, you can put them both in, it does the exact same thing both ways on both.
Yes, yeah. In fact, the pendulum one, it's even a little more unclear exactly what it means because you're moving the magnet, sometimes you're moving the magnet this way, sometimes maybe this way, and this way, and this way. So every point in that cycle would probably be driving current in a different direction around the ring. We could be a little more, we could be a little, I think you could find some example discussions of that on the book line. I will say that, let's say the magnet's right here, like here's a long pipe, the magnet's right here, it's like at my, like chin. The current in the section above the magnet and the current in the section below the magnet are not the same direction.
I guess, because the one has the change, the magnetic field changing differently on top and bottom.
The magnetic field's kind of pointing, let's say the North Pole magnet's
Yeah.
down, or whatever orientation you want to pick
So
for the
it's
magnet.
down and increasing.
It's down and increasing for the section of pipe ahead of the magnet.
Yeah, so it's induced upwards.
So what direction would current have to go around that section of pipe? It'd be going like around that direction. But then what if we apply the analysis to the section, just above the position of the magnet? It feels a downward magnetic field that's weakening with time.
Yeah.
And that means it wants to create more downward.
So it's the same.
It should be opposite. In one case, there's a
Oh, yeah.
downward field that's increasing.
So one's going this way and one's going this way.
And which one's which depends on if you drop it with the North Pole facing down or the South Pole facing down.
So how does that cause, what force is it acting on the magnet to keep from falling?
Yep, so let's say you had a coil. What do we say for the section below the magnet?
It's going that,
So now what is the magnetic
yeah,
field?
that way, that way.
Yeah, so now what is the magnetic field of this object's current? It's got an upward pointing like dipole moment, which means this is kind of like acting like a North Pole, and this is acting like a South
Oh,
Pole.
okay.
So this now acts like a magnet whose orientation is north to north with the descending magnet.
It's like it's a moving magnet.
Yeah.
The gravity's pulling down.
Yes,
the
but if we just kind of like paused it at one
Yeah.
moment in time, this section would be North Pole up and North Pole down. So what effect will this current have back on the moving magnet?
Yeah.
It'll be opposing it. And then what if you do the analysis again for the current above it?
It'll be a south pole going south.
It'll be a North Pole downward for the part of the loop above it,
Oh,
and it'll
oh,
see
pulling
us.
up. Oh, I see.
Yeah. So the direction of the current is opposite, but if we ask what effect the direction of the current in both cases is in whatever direction is needed to create like a braking force or a slowing force on the motion of the magnet.
So is that similar to the rings?
Yeah, and you could kind of look at that and you could say that's that's like the influences law. You could say it's trying to oppose the motion of the magnet, so it wants to be a North Pole up to oppose the approach of a north, or it wants to be a North Pole down to slow down, recession of a South Pole, and that's what they'll do. And actually, what would that mean about the section of pipe right about where the magnet is?
Nothing. Yeah.
It'd be kind of neutral. So like, it would, like the current would kind of die
On
out
the
towards
top
about
side,
zero
it's
right at
one
the
way.
midline of the magnet
Yeah.
and then build up.
Is it because there's two, on the top, one side, the magnet, or going, but it's still moving, or just, that is just so weak. It's not.
Yeah. So kind of, and you could kind of say something like, anyways, that would be true. Kind of in these pictures, like this section of the red magnetic field is not really changing much, but like here we're seeing it spraying it wider, which is anyways. So somewhere right along the midline of the magnet, the current will switch from, it'll die out towards zero at the midline and then build up in the opposite direction. Of course, way below the magnet, it's zero current, and way above the magnet, zero current, something like that. And those forces get stronger as the magnet moves faster, and they get stronger as the magnet moves faster. And at some point, those forces opposing the motion of the magnet are equal in strength to the mg weight force. of the magnet, and at that point, the free body diagram would be downward mg, upward magnetic force equal to that, and there's no net force, and it moves at a steady speed. And if it's going below that speed, gravity wins, and it speeds it up, and if it's going above that speed, like if you threw the magnet in there, it would slow the magnet down to its terminal velocity, which is very much like an air resistance. If you jump out of the airplane, you accelerate to terminal velocity and then you just drift downward. But if you fire a bullet downward through the air, it's going to slow down to terminal velocity and then fall at terminal velocity. All right. Yeah. Yeah. Questions?
Yeah, what class is this?
Yeah.
This is British lit. I wonder if British. So our syllabus is that British lit.
Yeah.
Yeah.
On the map of
Oh, I was born British lit.
Yeah.
Yeah.
You're looking for a quad 2 class?
Yes.
I'm not interested in this resume, but magnets, coil.